get started. I think probably will be a sketchy attendance today because of spring break, but let's anyway get started. So as you saw from my announcement on Piazza, we have put out the lab 1 grades. Okay, so take a look at your grade, but more importantly, take a look at the grade score feedback. Even if you get a good grade, don't ignore the feedback that's on grade score, because we have taken the trouble to give you some feedback without taking points off. Just you incorporate that. Be sure to take a look at that. If you have any questions, ask us. The regrade window is open. So somewhere in the middle of spring break. So if you have any questions that need our attention, please send those in before that regrade window closes. Right? We are done with processes, virtualization, and scheduling. Now we are going to look at a set of problems that are important in distributed systems, and we'll call them classical problems. Okay, so today we are going to talk about time ordering and clock synchronization. Okay, then we have in the next few classes mutual exclusion, which is distributed locks, distributed transaction, look at deadlocks, and end with the cap theorem. Right? So this is what would be the core of what you need to understand about distributed systems, a little more from a conceptual standpoint rather than the practical standpoint. But a lot of these ideas do carry over in all the systems that you build either in this class, okay, which is going to be clock synchronization. Okay? So I'll explain what is the problem, why do we need clock synchronization in distributed systems, and then we look at several different algorithms to perform clock synchronization. Okay, so we all know what clocks are and how we use clocks. Okay, so the move tell time when sun was directly overhead. That's how you define time. But now we have more time is, in some sense, we also have atomic clocks that are even more accurate, that tell us what the time is. Okay? So when you have clocks in any centralized system, and when events, let's say it's a single laptop or a computer, that's what I mean by centralized system, and there are events happening on that system, there is usually no ambiguity if we need to know something about the time at which that event or the order in which that event occurred. There are two events. If you compare their timestamps, you know which order they occurred. So that is never a problem in a centralized system. But now let's take a look at a distributed system of more than one machine. Okay? Each machine is going to have its own clock, okay? Because it has a machine has a real-time clock. That's how you can see that on your computer or on your phone or something like that. Right? So you might now want to compare time at which events occurred across machines, or reason about ordering of events across machine. Okay, this is going to require that the clocks on these machines are actually synchronized, because if the clocks are off, and then you look at a timestamp of an event that's on one machine and a timestamp of an event on another machine, you can't say anything about when that event actually occurred or the order, because the times may be off based on the clocks being off. Okay? So that can be a problem, and there are actual issues that occur in distributed systems, one of which is actually shown here. I think, I don't know if you can read it, but let me explain what the problem is. Okay, so essentially, we have, let's say, two computers. One is a computer on which you write your code, another, so that's your development machine. There's another machine that is used to actually build your code, or that's where you actually compile your code. Okay? In large software development environments, you have build machines because there are lots of files that you're trying to build, not just one or two files. So you separate set of machines actually doing builds, and then you write your code on your machine. So when you write your code and you're using, let's say, an editor, that file that you save to is going to get a stamp of when you modified it. That's the last modification time. Okay? And your build machines, usually what they do is they do incremental build. They don't build everything. They only build files that have changed. So they are going to look at the timestamp since the previous build, and only newer files since the previous build will be rebuilt. You're not going to go compile all 100,000 files on your project or something like that, right? So this timestamp is important for that build tool to know which files to actually compile and which ones not to compile. Those that have changed are the only ones that you got to recompile. Okay? But if the clock on your machine is off, okay, so then your timestamp that your machine assigns to the file is also going to be off, because it's going to just use the local time to say. So let's say your machine is actually has a very old clock value, meaning it's actually running behind real time. Okay, so you might save a file and it's going to get an older timestamp than the because your clock is off. Okay, when the build tool looks at it, if it had just done a build very recently, okay, you might actually get a time the previous build, okay, and then your file will not get compiled, and then your project is going to have some problem because you will not know why the changes you made are not being reflected in the code that was built. Okay, so these kinds of problems occur frequently because you have machines with different clock values. There is no guarantee that unless you do something extra, the clocks are all going to be the same or synchronized. They will never be the same, but they're synchronized. Okay, so that's the problem we want to solve. Okay, so I'm going to first give you a quick primer on clocks, and then we'll see how we can synchronize clocks. Okay, but is the problem clear why we need to synchronize clocks in a distributed system? Okay, using the simple example. Okay, so very quickly, this primer on physical clocks. How do we tell time? I already mentioned, okay, the time is basically astronomical metrics or a solar day. Okay, so essentially the time it takes for the Earth to rotate around its axis is 1 day. Okay, essentially you can watch that based on how the sun is, where the position of the sun is, and noon is defined to be whatever time the sun is actually directly overhead. Okay, so that's how in the old days you tell time. Okay, today you don't use necessarily the movement of the sun to tell time. You use atomic clocks or properties of atoms in terms of how they behave in order to tell time. And those clocks are essentially extremely accurate. They are accurate to 1 part in 10 to the 13, which means that you might lose a second every tens of thousands of years or something for that clock. So they're extremely accurate. Okay, so that's what we are going to use time. Now, if you have an atomic clock, how do you essentially tell others what the atomic clock value is? Because people are going to depend on that atomic clock to tell time. So usually what happens is there is maybe 1 or 2 atomic clocks that is the reference clock in most countries. And then the time that atomic clock is seeing is broadcast you over a wireless channel typically. Okay? So you can essentially buy a receiver that listens on this radio channel. It's really a radio frequency. Okay? So you can get a shortwave radio receiver that listens on that frequency, and then you can basically get the time, okay, because you're just listening. Okay? And you can set the clock on whatever your system is. Okay? And the same thing is true. There are other ways you broadcast now. You can use satellites to broadcast the time. Cell towers are broadcasting atomic clock values, and the atomic clocks are themselves broadcasting them. So if you listen to any of these broadcasts, you can essentially figure out what the time is and then set the clock. So that's how you can. Now, clocks that we have, okay, are not atomic clocks, right? It could be your mechanical wristwatch, or you might have a mechanical clock, which is not going to be very accurate. It will lose time every few months. You may be off by a minute or two. So it's not really. You can have quartz versions of those clocks. Okay, so quartz clocks essentially use the property of quartz crystals, which is how many times they oscillate in every second, to tell time, which is a lot more accurate than the older mechanical clocks. Okay? But even those are not going to be as accurate as atomic clocks. Even those might have inaccuracies, which we'll call clock drift. Okay, inaccuracies simply cause the clock to drift. That's what we are going to refer to as clock drift. So all real clocks we have at our disposal have to be synchronized with some master clock, which would be in our case, an atomic clock, for example, because periodically these clocks are going to run faster or slower than real time. They'll be off because of drift, and then you got to resynchronize. Okay, and this is no different from what happens on a computer either. Okay, a computer also has a clock, just as you might have a wristwatch. There's a crystal clock chip inside a computer that's also going to essentially be used to keep time, and that clock is also going to drift like any other clock. And so your computer clock will also go off if you don't synchronize it periodically. Okay, so that's the reason we need to now synchronize our clocks. Okay? So before we understand how to do clock synchronization, there's some very basic concepts that we need to understand, which will be the basis for actually designing any clock synchronization. That any clock that you want to synchronize, you know something about the clock, which is the maximum drift rate rho. Okay? That drift rate says what is the maximum value by which the clock will go off, okay, in some period of time, per unit time. Okay? That rho is going to be determined based on essentially what you have used to manufacture that. So for example, for quartz crystal, you can get a bound that says regardless of which quartz clock it is, a quartz property of quartz says that you can't be more than so much off by unit time. Now for any clock, you may be much less than that bound rho. But that's just saying that's the worst case drift that any clock that is technology might have. Okay? So we'll assume we know that worst case or max drift rate rho. Okay? So what that essentially says, two clocks with that same type of technology. Okay? The worst case drift for these clocks will mean that they might drift by 2 rho delta or 2 rho delta t every delta t time, because the worst case is fast, the other clock is running slow, so they're diverging from one another. Okay? So the maximum amount by which any two real clocks will be off, okay, if the drift rate is rho, is 2 rho times delta t. Okay? Because they're drifting rho every delta t time units. Okay, so not rho times delta t every delta time unit. So they'll drift by 2 rho. Okay, so that's basically the worst case by which you're off. Now, if you want to limit the drift to some value delta, okay, which means that you say I don't want to be off by more than 1 second, 1 millisecond, 100 millisecond. You pick whatever value you want to essentially say that's the inaccuracy I'm willing to tolerate. So that's our value delta. So see, we are saying we want the clock to be off by no more than delta. Okay? Me that value delta, then we'll say you got to resynchronize these clocks every delta over 2 rho seconds. So they are drifting by 2 rho. You want to limit the drift to delta. So you got to resynchronize them every delta over 2 rho so that they will essentially never be off by more than delta with respect to one another. Okay? So then this is pictorially shown in this figure where I don't know if you can read this or not, but the x-axis is real time. Okay? Y-axis is clock time. Okay? Now, if you had a perfect clock, okay, every time real time advances by 1 time unit or 1 second, your clock will also tick by 1 second. So you are in perfect synchrony with real time. Okay? That's this line here where the slope of that line is 1. Okay? So every time the time advances by 1 second, the clock also advances by 1 second. Okay? Now, most real clocks will not actually follow that perfect curve. They will be slower or faster. So essentially, if you are faster clock, then you have a slope that is greater than 1. So every time the time advances by 1, you are advancing by 1 plus rho. That's your that line has a slope less than 1, which means that every time real time advances by 1, your clock is going to advance by 1 minus rho. Okay? So essentially, you see them diverging here. So if you now resynchronize them every delta or 2 rho, the worst case clock drift will actually be limited to delta. Is that clear? Okay? Every clock synchronization algorithm you can find is going to use this basic concept. There's nothing more to it than that. Okay? You got to define what is the worst case drift rate rho for your clock. Okay? Then whoever is using this clock has to define what is the maximum value by which their clock should not be off. That's delta. So that's your error tolerance. And then you run the clock synchronization algorithm every delta over 2 rho seconds to synchronize that clock with some other clock or a master clock so that they are all synchronized. that clear? Any questions here? Okay. So if this concept is clear, then you can start designing actual clock synchronization algorithm. Okay? That's the basic concept, but now we'll try to design some real algorithm. The first one is called Christian's algorithm. Okay? Here we are trying to synchronize a computer, okay, a computer's clock with some master time server. Okay? We'll assume that there is some machine in the system which has synchronized with an atomic clock. Okay? So in this case, we will synchronize this computer with that time. So we'll call that the time server. Okay? We'll synchronize it with the time server. Okay? So what is the basic algorithm? Okay? So let's say there's a machine which is trying to synchronize itself. So every delta over 2 row seconds, because remember I said every delta over 2 row seconds, you got to synchronize. Okay? You know, delta is the maximum error tolerance, rho is essentially the drift rate. So every delta over 2 row seconds, machine P is going to send a request to the time server. You can send an RPC request if you want, saying what's the time. Okay, the time server is going to its current time on that machine based on whatever value came back. Okay, so every delta or 2 row, you ask what's the time, you get the time value, you set your clock. Okay, that's the basic idea. Okay, but it's not as simple as that, because you got to make sure that you are going to deal with message propagation time, because it's not like the message is taking 0 time to come over a network. Okay, in particular, that's shown in this figure here. The y-axis here going down is time. Okay? So you will see that there is process P. It sent a message saying what is the time. That message took some time to get to the time server. Okay? The first vertical line is the machine. Second vertical line is the time server. Okay, so you'll say, so you send a request at some time, it's going to get to the clock, the time server after some finite delay. That's the network propagation delay. And then the clock server is processing request. It looks at its clock saying that time is t, and it sends that value. And we assume that it takes a finite amount of time for that message to reach. So in this case, that time is t reply. That's the time it took for that message to return the server. So if you, because the message is not taken 0 time to arrive, right? So you got to correct for this. Okay, your question is. Okay, question is there a maximum distance between the computer and the time server that you should enforce, because it takes some time for that message to reach and you might be out of sync. Okay? There is no maximum distance. We are going to actually that estimate. If you can estimate the delay it takes for that message to go over the network, there is no problem, right? In particular, this clock value needs to be set to t plus t reply. Then you are fine. If you can estimate t reply, then the problem is gone away. Then you don't need to worry about how far the time server is. Okay? It doesn't matter how far it is. You should never just set the value to t, because that finite value is still going to put your clock off. Okay? So then the question is, how are we going to estimate the time it takes for this message to come back to you, okay, from the time server? Okay? So here's one idea. We don't actually know that value, but what we know is the time at which you send the request. You know the time at your local time at which the reply was received. So you know that time. Okay? That time is t request plus t reply. T request is the time for which the message took to go from the machine to the time server. That's the first message that went. T reply is the time it took for the reply to come to you. Okay? So you know the difference between the time you sent the request and the time you received. That you know. So the difference between the two is t request plus t reply. That's the entire time. Okay? So this is a known value, because you can. I sent the request to the time server at this time. I got it back 2 seconds later. It took 2 seconds for the message to go and come back. Okay? And we don't know actually what is t request and t reply. Those are two different values. As one approximation, we can assume they are equal. Okay? So one approximation is you say an estimate of t reply is t request plus t reply over 2. You just take the total value, divide by 2. Okay? You will say it takes the same amount of time for the message to go as it takes to come back. So we know the total time, so we'll divide by 2. That's an estimate of T request. Okay, so then we are going to T plus T request plus T reply over 2. And now we got one estimate of that correction. Okay. Now, as you can see, this is just an approximation. There's no guarantee that the message is going to take the same amount of time to go from the machine to the time server as it comes back. In fact, if you look at that picture, you will see that T request is actually bigger than T reply, and that is intentional, just to show you that they are not going to be equal in practice. But you did make some correction. Okay? Maybe you can make multiple requests to the time server, get multiple values of T request and T reply, get a approximate value that's more accurate than just one sample, and then use average across. So you can play all kinds of games to figure out what is a good value to use for T request. Okay? But by and large, you're going to take the round trip time, divide by 2. That's the one-way time. Okay, that's what we are doing. Okay, so you don't know the one-way propagation time. Is this clear? This is okay. Very simple problem, okay, which is you are going to take that basic concept I talked about in the previous slide, and every delta or 2 row, you basically send a request. Any questions on this? All right. So you're going to keep going. Okay. Here's another algorithm. Okay, this is called the Berkeley algorithm. The Berkeley algorithm, there is no time server. In the previous algorithm, Christian's algorithm, there's a master clock in the system. That's the time server. Every machine synchronizes with that clock. So then machines are synchronized relative to one another because they all synchronize with the master. That's the assumption. Okay? And we can say, what if there is no time server? How do we synchronize machines with them? Right? So these are decentralized. There's no central master to tell you what the clock values are, but there are n machines that want to synchronize their clocks. Okay? But there's no master clock in the system. How are we going to do this? Sorry? Can you pick anyone? Yes, you can pick anyone. You can say, we are all going to pick a random node and synchronize with that random node. That random node just happens to have a bad clock. Okay? Everyone is going to be dragged faster or slower than real time. Okay? But yes, could do that. They'll still be relatively synchronous. Okay? So what you can do is you can essentially ask every machine for their time. Okay? You get everyone's clock value. You take the mean of those clock value and say that that's the clock that that's the value everyone is going to set. Okay? So rather than picking one, you pick all. You get everyone's time. You take the average and say that's the clock. And some clocks will run faster, some will run slower. So if you take their mean, hopefully that value is closer to real than picking one random master. Okay? That's the theory. Now, of course, that's not guaranteed either. You might machines that are running faster, so it doesn't help at all. But if you have lots of machines, by and large, it might actually work fine. Okay? So here is how this works. Okay? So it's the same idea as last time. Every delta over 2 row time units, we will run this algorithm. Okay? So we will basically send a broadcast saying everyone needs to now tell what the time is. Okay? And then what we'll do is we will essentially, let's just take the top machine. Okay? It's basically send this request. Its clock is 3 p.m. The one that, okay, so we don't know what the real time is. And they just have all 3 different clock values. Okay? So you are going to ask for the value. Okay? So the one at the bottom, I'm 10 minutes behind you. The other one says I'm 25 minutes ahead, and then you tell yourself I'm synchronized with myself. And you take the average of these 3. You will see that the average is essentially 305. So you tell the one at the bottom to advance its clock by 15. You tell the other one to basically to come back by 20 minutes, and then you change clock to by 5 minutes. Okay? Everything I said in the previous thing is still two row. Still have to estimate network propagation latency, but we know how to do that. Okay? So I've not shown any of those extras here. This is just showing what you have added on top of what we already talked about in the previous two slides. Okay? So this is relative synchronization. No clock, no master clock, no time server. You just broadcast your time. Everyone broadcasts their time. You take the mean, and then you set your clock. And you have to correct for propagation delays. Okay? So every request, when you basically estimate the round trip time, so you know what the actual clock value should be. Is that clear? Okay, that's Berkeley algorithm. Okay, and there are many more. Okay, there are almost dozens and dozens of clock synchronization, but we looked at the two basic ones. I'll talk about one more. Yes. What if T reply is greater than the resynchronization interval? Okay, so first of all, that should not happen. You should not be synchronizing that frequently. So clocks are not that off, right? So typically, if you give delta and you look at rho, that will mean you synchronize every few minutes, every few hours. So you're not synchronizing every millisecond or something like that. Propagation delays, they are in milliseconds. That's how much time a message takes to go to another. So you are definitely not synchronizing every millisecond. That is just not going to be good because it just create a lot of extra network traffic. So we will assume that that is never true, that the resynchronization interval typically is larger than the propagation. And that's a reasonable assumption in practice. Okay? But yeah, if you have that condition, this will not work with you. Yes, question.
So whenever we are slowing or increasing the time, what happens?
Okay, so question, whenever we are increasing or changing the time, what happens to the processes that are running in that interval, right? The first thing is processes don't care about time. It's just that the clock value has changed. It's not like something ran and now we are deleted time or something. You are at time t. Okay, suddenly your clock value changed, but the process that was running is still there. Okay? So it's not like we are going to erase something that happened. You're just changing time. You're not changing what happened in particular intervals or something. Having said that, there is an important aspect of changing clocks that I'm going to talk about when I mention NTP. Okay? Yes, your question.
Is there an edge case where one process gets the time, another process gets the time?
Yes. The question is there a case where one process gets the time and then another process gets the time and there's some out of order? That can happen. Okay, and there are two cases there. What happens when the clock is advanced and what happens if the clock has gone backward? And the bad case is when clock goes backwards. Okay, that causes all sorts of problems. So since you asked the question, I'm going to jump ahead and mention this. So take a scenario example that was given. Your process reads the time. Okay, let's say you're doing your lab. Okay, in your lab, you are doing measurements of what were you measuring? The round trip time or the time it took for you to do queries, right? So how are you measuring it? You basically took the time, you take a timestamp, you send a request, then you wait for a response, you get another timestamp. And then the difference between the two is the time it took to run the query. Okay? So let's say you send the request at t, okay? And your request went, your machine ran clock synchronization algorithm, its clock went backwards, okay? And you got a response, and you'll find that the response came before you sent the request. So you got a negative response time. Okay? Not a good thing, right? Because that's going to cause problem. So anything that causes a clock to go backwards always causes problem, because if that actually happened when you are running your lab 1 experiment, you will get negative response time, which make no sense, but that's what actually the clock is telling. Okay? And lots of other things will go wrong if the clock always goes backwards. Okay? So you don't actually want that to happen. If it goes forward, bad things won't happen, but you'll just get a misestimate. Okay? Let's say you sent it at time t, clock went ahead by 1 second. Okay? You got a response. Your response will be 1 second more than what it actually is. Okay? You might say maybe the machine is slow, but it's not as bad as a negative response time, which is meaningless. Right? So some things are to be avoided, and particularly any clock synchronization algorithm that makes your clock go backward is always bad, because multiple things will get the same timestamp even though they were far apart in time, for example, right? We don't want that. Yes. Yes. Question is, if it's negative time, you know that something is wrong, but if you moved it forward, you don't actually know that you added 1 second. That is true. Okay? Machine not written assuming clock synchronization will start giving you a negative time, right? So that's not an exception you will have in your code. So if you use that to actually your applications will start making incorrect decisions, right? So yes, you won't know that, but most you will never write code thinking, maybe I should add a case where clock is actually going backward. Nobody will assume that, right? So that's not something you do. So you don't want that to happen. In any case, the time by which clocks move is very small. Nevertheless, these problems can occur, right? All right. So let's talking about network time protocol. So this is the protocol that most computers will use to actually synchronize themselves. It's called NTP, or Network Time Protocol. It's one of the more accurate time synchronization protocols to get. By accurate, we mean that it will ensure that your clock is not going to be off by more than 1 to 50 milliseconds. Okay? They're still going to be off. Okay? But it will guarantee that that's essentially going to be not off by more than 50 milliseconds. What that also means is the estimate of the network round trip time cannot be off by more than 50 milliseconds. That's all it means. But the error is coming from a network estimates. All right. So how does this work? So it's basically using Christian's algorithm. Okay? We already know what it did. It went to a time server, it got a response. Okay? And then it corrected for those estimates, except that it's going to do that 8 times, get 8 estimates. Okay? So basically you have A is the machine that is making the clock synchronization, B is the NTP time server machine. So you're going to basically, that's your T request, that's your T reply. Of course, there's some time here for the machine to process your RPC call, which we are also going to assume is part of that T request plus T reply. But you are going to make this 8 times. You're going to get try to get a good accurate estimate of T request plus T reply divided by 2 and try. Second thing you're going to do is, if after you get that estimate, you find that your clock is actually needs to go backwards, you will not set it. Okay? So you will never set a clock back. Instead, you will slow it down. So if you want to essentially move the clock back by 2 seconds, okay, you will essentially start ticking your clock slower, which means every 2 seconds you will tick it by 1. So your clock will catch up to real time rather than setting it back. Sorry, I said the opposite. You will take it faster, not slower. Okay, so you basically are back, so you are going to take it faster, so you will catch up to real time. Okay, so that you will never set the clock back. Okay, you want to basically synchronize by making the two be the same again. Okay, so is that clear? Okay, so that's the other thing. And then there is should go back. There is a hierarchical notion to NTP where NTP can have multiple time servers. So there can be a master server, and then there's a second level server that's synchronizing with the master. There's a third level server that's synchronized with the second level server. You can essentially synchronize with any of these, okay? And it still guarantees you that 50 milliseconds. So it is ensuring that then the delays don't add up, because if each one is off, then you will have a linear propagation of delays if you are synchronizing with a time server that is itself synchronized with 2 or 3 time servers hierarchy. So it has the notion of hierarchical synchronization, which we will not go in. Okay? But it has all of those concepts. What that means is, in a larger organization, you just need to have one time server, and then you can set up other time servers that sync with it, and your computers are syncing with those times. Okay? So you need essentially one that is listening to satellite, because the main time server needs to listen to satellite signal or listen to an atomic clock to synchronize itself. Okay? Others can just synchronize with that machine. Okay, so that is NTP. Okay, main concept: clocks can't go back. Okay, you essentially want to make sure that you are going to adjust the clock by making it go faster or slower. If you are going faster, you don't really want the clock to jump either. So if you are ahead, you slow it down so time catches up with the clock. If you are behind, you speed up the clock so that your clock catches up with time. You do those things, and then you're fine. And then you let the clock tick at the regular rate after that. Yes. No, you don't have to immediately. I mean, that's just the same as jumping, right? If in 1 second you take it by 1 minute, let's say you're off by a minute, right? So you want to assume that it will catch up fairly quickly, but you don't want to do it in 1 second or something. That's just say. Oh, yeah. So question is, does it have to catch up by the time you run the whole algorithm again? That's what you're asking. No, you don't have to wait that long. You can catch up much faster than that. Okay? Or you don't, you just decide what's the good value. Okay. All right. So that's NTP. Okay. So now we are going to talk about another way of doing clock synchronization that is based on GPS. Okay. You probably know what GPS is. Called global positioning system. Okay, that's what you use to get directions on your phone when you're going somewhere. Okay, Google Maps, Apple Maps, they all use GPS, and then they use a mapping tool to essentially tell you where you are. But as we will see, GPS is another way by which you can also do clock synchronization. It does that. Okay, there are GPS receivers that have nothing to do with cell phones. But you could, in the old days, just buy a device that was a GPS receiver. Okay? It would just listen to GPS signals, which are satellite signals, and synchronize and tell you what the location was. Okay? Now, all these GPS are built into phones, so you essentially can use the phone itself as GPS receiver and use it to get directions and so on. Okay? But let's try to understand the concepts. Okay? This requires some basic, very basic geometry background, okay, which is all really high school background, so you'll all understand what I'm trying to say here. But we need to figure out what the how GPS. So here is basically the basic idea. Okay, so let's say in the case of GPS, what you have are your satellites that are at known locations in the sky. Okay, so there are some number of satellites. Okay, and these satellites are essentially, we will assume that they are already synchronized with atomic clocks. So these satellites are clocks that are already synchronized. So they're atomic clock. And these satellites are simply broadcasting their location. Okay? Let's say, just for now, forget the time for just a second. Let's say each satellite is at known location. So satellite 1 is at some coordinate X, Y, Z in the sky. Some other one is at X prime, Y prime, Z prime, and so on. Okay? So they are essentially broadcasting their locations and time. So for now, let's just assume that you are listening to the satellite signals. Okay, so we for just a second assume that some receiver on the ground has figured out that it is a distance d some satellite. Okay. Okay, so just for a second, we how to get that d, we'll just see this. Okay. If I know that I'm at a distance d from a satellite, what does it tell me? Does it tell me anything about my own location? Tells you something, but doesn't tell you what more exactly. No physics or waves here. Okay. So if I just tell you, okay, I'm 1 kilometer away from you, what does it tell you about where I am? Just friend says I'm 1 kilometer away from you. What does it tell you? It just tells you are on some circle of 1 kilometer radius. That's all it tells you, right? So if I know that I am at a distance d from one satellite, it just tells me in 2-dimensional space for just a second, not 3 dimensions, that I'm on some circle at that distance d. Okay? I don't know my exact coordinate. I know the coordinate of the satellite because that's a known location. Okay? But I don't know where my coordinates are at the moment because I just know I'm on a circle at that distance. Okay? But let's say now I listen to another satellite and I say I figure out I'm at a distance d prime from that satellite. Okay? Same thing. Now I know that I'm on some circle at a distance d prime from that satellite. Okay? Now my location is fixed. Okay? I have to be at the intersection of those two circles because the only intersection points are simultaneously at a distance d from the first satellite and a distance d prime from the second satellite. Okay? This is why, so this says that this, whatever this receiver is either at that location, which is the first point of intersection of the satellite, or the second point, because those are the only 2 points that can be at distance d from this point here and distance d prime simultaneously. Okay? Those are the only points for which both of those conditions are true. Every other point will only have one of those conditions on the circle. Okay? So now I have actually reduced my coordinates to one of two finite values in a circle. I know that I can be at any of these 2 locations and no other location. Okay? If I had a third satellite, I would be done. I would have another circle and hopefully it intersects with one of these and I'm done. Okay? But even these 2 tell you something. Okay? So we are basically going to use property of geometry, which says that we will estimate distance to satellite. Okay? In real world, that will put us on a sphere, not on a circle, because real world coordinates are 3 dimensions, x, y, and z. Okay? So if I say I'm at a distance d from someone, I'm not on a circle, but I'm on a sphere. Okay? Clearly, I'm not in the sky, I'm on the ground, but still I'm on a sphere. Spheres, and we are going to intersect them, and then the same concept, right? So you intersect 2 spheres, you get a circle. If you think of 2 balls and you just them, you'll get a circle. So you are anywhere else, which is this, and then you are down to 2 points. So that's what we are going to do. But we will use some coordinate geometry. Okay? Still haven't said what clock synchronization has to do with this. Okay? This is just positioning. Okay? This is how any positioning works, by the way. We have what are called landmarks, which are known location, distance to the landmark to find your location. Okay? That's how you find position. So you say, I know the coordinates of that famous thing. That's how you give directions as well, right? So you must know where some famous landmark is, go there and do something. Right? So that's how it does. This is how you estimate distance as well. Right? So we'll now figure out how to do this in 3-dimensional space. So we will assume the following. Okay, maybe I need to draw a picture for this, and then we'll go back to equations. So let's do this. All right, so here, that's satellite 1. Okay, x1, y1, z1. Okay, here is our user, okay, who's trying to find their location, x, y, z, unknown. Okay, x, y, z is unknown. Satellite is at a known location in the sky. Okay, so the satellite is going to. So how do you find your distance to the satellite? The satellite is sending out packets, okay, with timestamps on it. Okay? So you basically say, let's say packet started at time t. Okay? It was received at time t prime. Okay? The packet came with some timestamp in it. Okay? So you know that the packet took time t prime minus t to come. Okay? That clear? Does that give you distance d? How does it give you distance d? That's time. T dash minus t is took for the packet to come. Doesn't give you a distance yet. Yes. Yes. So this packet is basically wireless transmission, right? All wireless waves go at speed of light. So this is the distance d is speed of light times t prime minus t. That's your distance. So now I know the distance. So that puts me in a sphere. Yeah, because I said I know the distance to a known location, that's d. So I'm on a sphere with center x1, y1, z1. Correct? All right. We'll do this again. Another satellite, x2, y2, z2. You listen for yet more broadcast. Another satellite sends you a broadcast. Okay, that one, let's say, is we'll call this t double prime. And I guess we can't call it t, but we'll call it t2 or something like that. Okay, so this distance is c t double prime minus t2 or something like this. And this is is a different distance d. Okay. So now we have located ourselves on two satellites. Okay. Still we don't know what our coordinates, but we know one more quantity which we have not used yet. Okay. We know what the value of x1, y1, z1 is. That's a known location. Okay. My coordinates x, y, z are unknown. Okay. But I know the Euclidean formula of distance between 2 points. Right. So that should be square root of x square plus y1 minus y square plus z1 minus z square. That's d. Right? Is that clear? These two values should be the same. Okay? So C, this is a known quantity, right? Because I know t prime, I know t, I know the speed of light. Okay? So I know this distance, and that is the other distance. So essentially I got an equation with 3 unknowns. Okay? Not a linear equation, but still an equation. Okay? Because I just equate the two. Okay? The equation with 3 unknowns, that you can't solve that equation. But I can do this with multiple satellites. So this will give me another equation. This will be x2 minus x square plus y2 minus y square plus z2 minus z square. Square root of that is this other distance. Okay? So I basically construct multiple equations. I need at least 3. There are 3 unknowns. Okay? And then I solve for it. I will get x, y, and z. Is that clear? Any question on very simple geometry here? I just construct these equations and I solve. Okay? But there is a problem which we haven't yet figured out, which is, okay, you are using clock on this GPS receiver to estimate the distance. Because I said that the packet left at time t from that satellite, it arrived here at time t prime. Okay? This entire exercise is only accurate if t prime is an accurate estimate. If t is off, then you're going to get some bad distance. Because my clock is 10 seconds off, it'll look like you're really far away from the satellite because it looks like the distance is really long. Is that clear? So unless this clock is synchronized, okay, with something, that estimate is going to be off. So how do we do this? Could say let's synchronize with something else, problem is solved. Right? That's one value. Okay, but there is nothing else here. I only showed you some satellites and a receiver. That's all we have. Yes. Yes, it is sending the timestamp. It's always sending timestamp. Every time it sends a packet, it says this is the time at which I sent it. Okay, and I receive that packet at some later time. That's the speed of light propagation delay. Okay, so let's say you send it at noon. I receive it at noon times whatever, 10 milliseconds. So it took 10 milliseconds to come. Okay. Yes. Yeah, you can receive as many packets as you want. There's no problem. You can do whatever you want. Yes, that's the real answer. So we will assume drift is actually an unknown. There are not 3 unknowns, but 4 unknowns. There's your coordinate, the time by which your clock is off is the 4th unknown we will add. So we'll add a delta is another unknown. Okay. So now this distance is not actually known to us because there's an unknown in that distance. So there is actually a minus delta there. Okay, because that's the time by which you're off. And t minus delta, however you want to put it, because as a delta time term is unknown, y and z are unknown. Okay, so there's equidistant. Okay, these two distances are the same, still an equation, but that equation has 4 unknowns, not 3 unknowns. Because the clock synchronization is actually part of solving a positioning problem. So you can't do this with 3 satellites. That's the minimum number. You need at least 4, minimum of 4. Okay? But actually more than 4, but it at least has to be 4 equations to solve 4 unknowns. Okay? But remember, these are non-linear equations. Only if it's linear equations with 4 equations, you get actually a solution for that equation. Because in non-linear equation, essentially you will need more than 4. because there will be multiple solutions. It's not a linear, with not at one point, right? So you will essentially get the same problem. But there are many satellites. So most GPS coordinates will need at least 6. With 4, they'll not get a good lock because that does not give them a good estimate. But 5, 6, they start getting a good estimate. Okay? So, but you need at least 4. Okay? So we solve for delta as part of solving for x, y, and z. And then we are done. We found the position of the GPS receiver, and we found the clock drift that we use to correct for the actual timestamp, and then we find the essentially the actual location. Okay? That's how GPS actually does it on your phone or any other device. Okay? So part of every GPS is essentially a clock synchronization that is. Hold on one second. Okay, so this is basically a recap of whatever I said. Okay, so the delay that you are essentially going to see is t now minus t plus the clock drift, that is actually that delta, but it has slightly different term here. Okay, distance is t now minus ti. Okay, but that you have to add that thing there, and here is the other distance formula, that's square root of xi minus x squared and so on. Okay, so these two values are the same. So you set up these 4 equations, solve for 4 unknowns. Okay, and hopefully more than 4. Okay, so we looked at Christian's algorithm, which had a time server. Then we looked at Berkeley algorithm, no time server, set the value to the average, and looked at NTP, which used Christian's algorithm, let the clock make happen. And you looked at GPS, which always solves for a clock. Yes. So 4 different techniques. Any questions on this? We are going to switch gears and go into another concept that's slightly different. Also synchronization, but different approach. All right. So yes, go ahead. Okay. Are the satellites moving? All right. So that's a good point. I should have mentioned this. You have to have geostationary satellite. If it's a moving satellite, you can't do this, and their position is unknown. Okay. There are lots of satellites that will move. Those are not the satellite. You want a geostationary satellite. So with any point on the ground, it's actually at the same location. Okay. It has to be at a known position. Otherwise, this will not work. Okay. I hope people know what geostationary satellite means. If you are far enough, you will move at the same rate as the Earth. So you will essentially be at the same position. You're not going to move. Okay. All right. So I'm not going to do wireless synchronization. I don't know why this is. But we'll talk about logical clocks. Okay. So now we looked at all kinds of practical clock synchronization algorithms. But the one thing that we have not addressed is that it will always have some error in them. The error comes because there is some error in estimating the propagation delay, the network propagation delay for most clock synchronization algorithms. That's never going to be exact for us because we are using t request plus t reply over 2 as some estimate. And no matter how many times you do this, there will always be some minor difference for the forward propagation and the reverse propagation that will introduce some error. So all clock synchronization algorithms will have some error bound. They'll say this clock synchronization can guarantee you at most, like NTP says, you will maybe off by 50 milliseconds. Okay? That's the so if you have 2 events that have occurred on 2 machines that are within 50 milliseconds of one another, you have problems. You can't actually tell which one happened before the other one because the clocks are off by at most 50, at least that's the bound by which they're off. So you are not going to be able to figure this out, right? So if there are events that are occurring very close to one another and that is closer than the error tolerance of the clock synchronization algorithm, all bets are off. You cannot use them to figure out the distance, time between those two or the order. But if they're more than the error tolerance, then you can do everything. So in some sense, for most practical certain boundary case, events are occurring very close to one another, does not work very well. Okay? So we want to figure out, can we get around this problem and not actually have to worry about the error in clock synchronization algorithm. Okay? That brings us to this concept of logical clocks. Okay? So logical clocks are essentially like real clocks with one difference. They only allow us to reason about order of events, not the time difference between events. Okay? Real clocks give us two properties in distributed system. Okay? Given two events, you can figure out the time between those two events. So for example, you figured out the round trip time on your lab 1 by checking the time at which you sent the request, time at you got, using time for two different things, to estimate delays and to estimate order. Okay? When you are trying to do software builds, the make tool or the build tool is looking at timestamps to determine order. Did the file change after the previous build? Okay? It doesn't matter whether it changed 1 second after, 1 minute after, 1 hour after. So long as it changed after, that's all that matters. Right? So in some cases, only the order matters, not the distance between the events, but in some cases, the distance matters. Logical clocks is only going to be useful if you are worried about the ordering of events, okay? Not the time delay between two events. For that, you need physical clocks. Okay? But if, for a large class of problems where only the order matters, these are going to give us some properties that do away with issues with clock synchronization. Okay? So essentially, here is the basic idea. Okay? So we'll assume that clock synchronization. So here we will say, let the clocks of these machines not be synchronized. We don't care. Okay? They may be off by arbitrary values, but we are not going to be worried about real clocks at all. Okay? Our logical clock is going to be an integer, which is actually, we'll see how to use that properties. Okay? So essentially, this is going to be used when processes need to agree on the order of events. Okay? So here is the basic idea. Here's the problem, first of all. Okay? We are given a set of events in the system. Okay? Doesn't matter what those events are. And we want to just find the order in which those events are. Okay? The real time at which those events occur is not material. These events are occurring on different machines, not on the same machine. Okay? If it's on the same machine, there is no problem because you can just use the local clock and get timestamps. It doesn't matter whether the clock is off or not, because since the clock is ticking, if one event gets a later timestamp, it must have happened after the previous event, even if the clock is off, right? Because the relative distance between the timestamp tells us the order of the events. Okay? But when the events are occurring on different machines, then you can't use the actual timestamps because you said clocks are not synchronized, explicitly said that. So you can't say what was the time on that machine when that event occurred and what's the time on this machine. Try to compare it, meaningless, right? Because clocks are not synchronized. So we will assume clocks are unsynchronous. Global clock means there's no master clock in the system. Okay? So we cannot order events on different machines using their local times. Okay? So what can we do? Okay? So a basic idea that we are going to use is that machines, not machines, other applications in this distributed system are going to exchange messages. They're going to communicate. It is a distributed system after all. It could be a client or a server or some other set of peer-to-peer applications. They send messages. Okay? We will try to find the order of events, okay, in this system just from this message exchange. Okay? No other property. Okay? We'll just use the fact that these processes are communicating to find order of events. So what can we do? Okay, so what property can we get that will allow us to do this? Okay, this was a idea that was proposed by Leslie Lamport. Okay? He's a very well-known researcher in distributed system. We will see many techniques that he proposed in the next several classes. Incidentally, he's also a person who designed LaTeX. Okay? LaTeX, if you know what the term means, it's Lamport's tech. Okay? This is Leslie Lamport of the LaTeX fame. Okay? We'll talk about LaTeX here, but we'll talk about his logical clocks, also called Lamport's clocks, because he is the one who proposed this idea. Okay? So what idea can we use to determine ordering of events? there's only one property we need to use about message sending. Okay, so when a message is sent, there are two experiments that occur. Okay? There's a sending message on process 2, possibly on some other machine. So that's essentially that's a message that you send. You send the message from one machine. At some later time, it arrives at some other machine. Right? So, okay, because the clocks are out of sync, they're not synchronized. The only thing we know is that regardless of the actual clock value, the send must happen before the receive. You can't receive a message that has not even been sent, right? Because that is essentially what physics dictates. So sending of an event must have occurred before the receipt. So sending of a message must have occurred before the receipt of the message. Okay? Sounds like a very obvious thing, okay? But we'll use that to derive lots of interesting properties. Okay? So before we do that, we are going to define a relationship that actually allows us to derive that property, which we'll call the happened before relations. A very simple idea. So we'll say if A and B are two events, okay, any two events, and for the moment that have occurred, okay, and if A executed before B, okay, then A happened before B. So let's say a process is executing something. Okay, it is making two print statements. These are the events we care about. Okay, the first print statement is executed before the second print statement by the process. Clearly, the first print statement is happened before the second print statement. Okay? Because that's execution order. Execution order, you got one instruction executed before the other one. That instruction happened before the other instruction. Okay? Very obvious. That we know. Okay? Now, message and B is the receipt of this message in some other process. Okay? Those two events are also ordered. Okay? Because the send has happened before the receive. So in this case, A has happened before B. Okay? So within processes, events are ordered by execution order. Okay? Depending on order you execute, you can order events. Across processes, order them by send and receive. Okay? If you send from one process, you receive it in another process. Okay? And we will now make this a transitive property, which says that if A happened before B and B happened before C, if you know this, then A has happened before C. Okay? That's a transitive property. So within a process, if print 1 happened before print 2, or you executed print 1 before print 2, and you executed print 2 before print 3, then the transitive property holds that print 1 must have executed before print. Right? So same is true for send and receive and things like that. Okay? That's all we will use. Okay? Very simple ideas. Okay? Execution order is defined. Okay? Send and receive is defined in terms of ordering, and we will assume that we will use transitivity property. I'm going to picture here. Let's try to get green. So here I'll draw a picture. Okay, this is process A. This is process B. Okay, let's say there are some local events here, okay, which are just indicated. That's execution order. So we know those. Okay, because that's the order in which you're executing. Okay, let's say at some point A has sent. Okay, so we'll have some other local events here and then here. Okay, this is the send. This is the receive. Okay, the send has to happen before the receive. Regardless of clocks on processes A and B, okay, you cannot receive a message before it's sent. Okay, so those two events are ordered. Okay, so now because this is local events, okay, all of these events are ordered with respect to that send. They have happened before the send because that's execution order within that process. Okay, and now all the local events on B after the receive are also ordered with respect to receive because they are executing after the receive. So these events are now ordered with respect to the receive. Transitive property holds. So what that means is the events are circled in A happened before the events are circled in B. Okay? Because all of the events in A happened before the send happened before the receive, and the events on B after the receive have happened after the receive. So now we've taken some events in A and some events in B, and now we ordered them. There's no clock, no timestamp. We just use simple obvious properties of how processes execute, how messages are sent and received, and okay, that's our happened before relation. Is this clear? Okay, it's a partial ordering. Okay? Because if I now ask you, if I show you saying, okay, look at this event and this other event in A and B, can you reason which ones happened in what order? You'll say, okay, the event in A has clearly occurred before the event in B because I can see a transitive relationship between those events. Okay? But if I say, what about this event in A that I circled, and then there's another one in B, which I put a square on. Can you say something about that? Okay? That relationship is undefined. There was no message exchange between A and B that allows us to order that event in B with respect to that event in A. So these two events are said to be concurrent. I don't know their ordering. We don't have real clocks. We don't have real timestamps. So I can't figure it out. Okay? But whenever there is a message exchange, everything before the send gets ordered with regards to everything after the receive. Okay? So, and you can have multiple messages. Right? So you can have another message going from B back to A, and you can have B sending a message to C. Okay? And then you have essentially some events on C, which is here, okay, which have now got ordered with respect to A. Even though A and B have not communicated directly, A sent a message to B, B sent a message to C. The transitive property still holds because those events have happened before the send happened before the receive. This receive has happened before this next send, and then there is a receive here and so on. So now I can actually order events across processes and across machines, even though they did not directly communicate. They indirectly communicated through some other machine. Okay? No timestamps. We are just looking at this picture and saying, okay, now I can figure this out. Is this clear? So this is our happened before relationship. Okay? Now we want to derive an actual algorithm that will allow us to figure this out. So this is just a picture. Okay? How do I realize this in code and say, okay, that event has actually happened before this event? I need some way to do this, okay, which is what we look at. Just a second, I need to redo this. Seems to make some mistake every time I set this up. Okay. All right. So algorithm that allows us to get that happen before property. Okay. So this is where we are going to get back to our logical clock. Our goal is defined there. Okay. We want to define the notion of a logical clock such that if event A has happened before event B, you are given that, then the logical clock value we assign to A has to be less than the clock assigned to B. Okay? And if A and B are concurrent events, you are told that, then it doesn't matter what clock value you assign. So when the events are ordered by happened before, make sure the clock timestamps actually reflect that happened before. The one that happened is first has to have a lower clock value. Okay, what's a simple technique to do this? Okay. Here is what we are going to do. Okay. We are going to keep an integer variable with every process. That's going to be its logical integer. Okay. No real time. Okay. The real clock is doing whatever it does. Okay. Every time a local event occurs that you care about within your process, any event that you execute within a process that you care about, you take your local clock, you take that integer by 1, you increment it by 1. Okay. So every process in the system, there are n processes on maybe n machines. Every process is keeping an integer that's logical clock. Okay. And every time it's doing something it cares about, a local event it's occurred, you increment your integer. Okay. Then say that this process sends a message to another process. Okay. In addition to the message, you are going to send your current clock value, which is that integer. Okay. So you're going to send it. Okay. So that's basically the send time, not real time, but logical time of the send. Okay. Then you receive that message. When you receive the message, you take the max of the send clock that came from the sending process, your clock, you take the 2 and you do +1. This will always ensure that the receive event gets a clock value greater than the send. Right? Because you take the max of the 2 plus 1. Because if you didn't do the max, your local clock may not have advanced as much as that other clock. Maybe the other process already has a logical clock of 100, yours is set to 50. If you simply take it by 1 saying a receive happened, then you got a clock value of 51. That's why the send has happened before receive. So I need to assign a clock value to the receive that has to be greater than the send. So that's why I take the max. I say you send me your clock value, I'll take your clock value, mine take the max, and then say plus 1. This always guarantees that the receive event will get a clock value greater than the send, no matter what the actual logic. And then you continue. And that's all, right? So that's going to give us that property. Okay, so you will maintain your logical clock, this integer. Whenever a local event occurs, increment by 1. When you process I sends a message to process J, you send your clock value. Okay? When J receives that message, okay, if your clock is always already higher, then otherwise you will do the max. Okay, is this clear? This is going to give us that property examples, and we'll try to see what happens. Okay, so there are two cases here. There is process P1, P2, P3 in the first figure, the same 3 processes in the second figure, and we'll see some messages going back and forth. The values are logical clock values that are at different points in time. So every time you send that message, okay, you got to send your clock value. And when you receive the message, you take that clock value, take the max of your clock, that clock plus 1. Okay. So you will see here, okay, there's a P3 has sent a message at time, it's logical times 60. Okay. So that is going to go with the message. When that message arrives at P2, its logical clock is only at 56. So if it increments it by 1, it goes to 57. You just violated our condition because your receive has a lower timestamp than the send. We said that send always happens before the receive. So receive has to have a greater timestamp. So this has to be max of 56 and 60 plus 1. So you will see here that this is when the actual technique was. So you actually incremented that not to 57 but to 61. Okay, so that's one condition, and there's another M4 that has the same problem, where if you had sent this, basically this one is at 54, you will get the incorrect value. But if you run it here, you'll see that because you adjusted that, this became 69, you sent it, so that has actually become 70. Okay. So if you do this, shall ordering of event. Okay? So now if I ask you, if I give you 2 random clock values and say, given this clock values, what can you say about the ordering of events? What would you say? If I say P1 has an event 18, okay, P2 has an event 40. Okay, if I just give you these clock values, what can you say about these? So the answer is going to be, it depends on whether you show me this picture or don't show me this picture. Okay? If you show me this picture, then you will say that 18 and 40, okay, are concurrent events because there is no send between 18 and 40 that allows everything before the send of M1 gets ordered with respect to everything after the receipt. Okay? But 40 has actually happened after M1. There is nothing that is gone. Okay? So you can't actually compare 18 and 40 and say that what in what order those events occur. Okay? But suppose I did not give you that picture. I just said, here are 2 clock values. Can you compare them and tell me which one has occurred before which other? Okay? Answer, you cannot say anything because I'm just giving you 2 random numbers and saying, tell me what happened. Okay? If it was physical clocks and their clocks were synchronized, you would say, okay, time 18 is a time that's lower than 40. So that event at 18 has occurred before 40, assuming the clocks are synchronized. Here clocks are not synchronized, so I can't say anything. Right? So in essence, what we have done is we solved half the problem. Okay? We basically said, if I tell you the happened before relationship, we have derived a time stamping algorithm that gives me clock values that respect that relationship. But if I give you two clock values and ask you to reason about happened before relationship, if A happened before B, that is implying that the timestamp this assigning essentially respects that value, which is clock value of A is less than clock value of B. But what we want is the opposite property. Okay? We want to be able to take two timestamps and look at them and say that based on these two timestamps, which one happened before which other one. That's what physical clock gives us. You timestamp two events, I look at those clock values. If you are synchronized clocks, then this must have happened before this because this is lower value. That we don't have yet. Right? So we need to now solve the other problem, which is the opposite implication. So we have to now extend this algorithm to get us the other half of it. Okay? We only solved one half. We have a time stamping approach, but we cannot compare the timestamps. We want to be able to compare the timestamp, not just timestamp. Okay? So that's going to be next time, not today. We ran out of time. Okay?